Welcome to the course on error control coding and introduction to block codes. Today we are going to discuss on bounds on the size of the code. So let us say you know the code dimension information sequence length and you know the minimum distance of the code. You would like to know, for example, what is the minimum number of parity bits required so that you get that guaranteed minimum distance of the code. So a code, as we know, can be described by parameters n, k and let us say minimum distance of the code. So if we specify any two of these parameters, we would like to know what would be the third parameter. For example, if I specify the minimum distance of the code and the information sequence length, I am interested in knowing what is the minimum number of minimum n required so that I get this k and d, okay. Or let us say if n and k are specified, I am interested in finding out what is the maximum minimum distance I can get. So fixing two parameters, I am interested to know about the third parameter, and in this lecture we are going to talk about bounds that link these three parameters. So in particular we will be talking about Hamming bound, and we will introduce the concept of perfect codes. Then we will talk about singleton bound, and the codes that satisfy singleton bound are known as maximum distance separable code. We will talk about them. Then we will talk about Plotkin bounds and Gilbert-Varshamov bound. So as I said, we are interested to find the largest code word of length n and minimum distance d. So knowing those two parameters, we are interested to know what would be the third parameter, and in this talk we are going to talk about bounds which will give us upper bound and lower bounds on those parameters. So let a and d denotes the number of code words of length n and minimum distance d. So we would like to know how many such code words exist which have code word length n or minimum distance d and minimum distance d. Or in other words, we could also pose this problem like this: we are interested to find the minimum number of parity bits required. So given that we know k and d, we would like to know what is the minimum n required, such that we can get those k and d. So answer to these questions basically we will pose and we will try to get some bound on those parameters. So if I give you two parameters, you should be able to, we are interested to know what is the bound on the third parameter. So what are the permissible value for the third parameter? So we will start with Hamming bound. So what is Hamming bound? So the Hamming bound says for a binary nk linear code whose minimum distance is at least 2t plus 1, okay, the number of parity check bits satisfies this relationship. So if you have a linear code whose minimum distance is at least 2t plus 1, then number of parity bits must satisfy this. So number of parity bits are lower bounded by this. So how do we prove this? Now if we are interested in a linear block code whose minimum distance is at least 2t plus 1, we know from the property of linear block code that this code can correct t errors. Okay. A code which has minimum distance of at least 2t plus 1 can correct t errors. Now if we look at our syndrome decoding, recall if we want to correct t errors, all these error patterns of weight up to t should be the coset leaders. Then we can correct these error patterns. So, if a linear code has minimum distance of 2t plus 1, which means all error patterns of weight up to t are correctable, and hence we can use all weight patterns of t or less weight as coset leaders. So, all error patterns up to weight t can be used as coset leaders. Now, let us count how many such error patterns are there. So, let us look at how many error patterns of weight 0 are there, that is given by NC0. How many error patterns of weight 1 are there, that is given by NC1. So, how many error patterns of weight 2, that is NC2, and similarly how many error patterns of weight t, that is NCT. So, these are the total number of error patterns of weight 0, 1, 2, 3 up to weight t. Now, note all of these should be the coset leader, then only we can correct them. But what is the maximum number of coset leaders possible? Now, that number we know is given by 2 raised to power n minus k. So, these are the total number of coset leaders we have. Now, we want all of these error patterns to be coset leader, then this number should be less than 2 raised to power n minus k. Hence, we get this condition that total number of coset leaders should be more than all error patterns of weight up to t, and hence if we take the log of this, we get this condition that n minus k is less than is greater than equal to log of this, okay. And that is basically our Hamming bound. Now, when is our Hamming bound satisfied with equality? Our Hamming bound will be satisfied with equality when all error patterns of weight up to t are coset leaders and no other error pattern is coset leader. So, when this is satisfied with equality, when this equation is satisfied, then this inequality is satisfied with equality, then we have Hamming bound satisfied with equality. So, a t error correcting code is called a perfect code if it satisfies Hamming bound with equality. And when will it satisfy Hamming bound with equality? When its standard array has all error patterns of t or fewer errors and no other error pattern as their coset leader. So, it is important, no other error pattern except all error pattern up to weight t should be the coset leader. So, if Hamming bound is satisfied with equality, it is known as perfect code. Now, examples of perfect code is, for example, single error correcting Hamming code or triple error correcting 2312 Golay code. Now, I just want to caution you that perfect code does not mean that these are the best possible codes. Okay. So, do not confuse perfect code as the best possible error correcting codes. The next bound that we will talk about is singleton bound, which gives an upper bound of on minimum distance. So, it says the singleton bound says that a minimum distance of an nk linear block code must satisfy this inequality. So, minimum distance is less than equal to n minus k plus 1. Now, how do we prove this? So, for an nk linear block code, we have an n minus k cross n parity check matrix. And what is the row rank of the parity check matrix? That is n minus k. Now, if the row rank is n minus k, then column rank is also n minus k. Now, if the column rank of parity check matrix H is n minus k, that means any combinations of n minus k plus 1, because the row rank is n minus k. So, if we take n minus k plus 1 columns, they must be linearly dependent, right. So, they must be linearly dependent. And what do we know? What is the relationship between the columns of the parity check matrix and minimum distance of a code? Now, we know that a minimum distance of a code is equal to the minimum number of non-zero columns in the parity check matrix that are linearly dependent. If you recall, we have proved that the minimum number of columns of the parity check matrix that add up to 0, then there exists a code of that weight. Now, so what we have seen is then n minus k plus 1 columns of H matrix, they add up to 0 because they are linearly dependent. Why? Because the column rank is n minus k. And if n minus k plus 1 columns add up to 0, that means the minimum distance can be at most n minus k plus 1. Hence, we prove that minimum distance of a linear nk code is upper bounded by n minus k plus 1. Now, the same thing we can prove in a different way. I will just give you an alternative proof of the same result. So, what is minimum weight information sequence, non-zero information sequence? So, if we consider minimum weight information sequence, that would be weight 1, right. So, the minimum non-zero information sequence weight is weight 1, right. Now, if we consider minimum non-zero information sequence, which is of weight 1, now how many number of parity bits we have? N minus k. Now, let us assume all n minus k of these parity bits are 1. Then what is the maximum possible minimum distance? That is n minus k plus 1, which is the weight of the information sequence. So, we cannot have weight more than n minus k. And since the minimum distance of a code is equal to the minimum weight of a non-zero code word, right. So, if you feed in a non-zero information sequence, the maximum output weight that you can get is n minus k plus 1, and hence the minimum distance of the code cannot be more than n minus k plus 1. Now, the codes that satisfy singleton bound with equality are known as maximum distance separable code. So, maximum distance separable code will have the property that minimum distance is equal to n minus k plus 1. And these are very good code, they have the maximum distance possible between the set of code words. Examples of maximum distance separable codes are repetition code, single parity check codes, Reed-Solomon codes. The third bound that we are going to prove is what is known as Plotkin bound. So, what does Plotkin bound says? That minimum distance of an nk linear code satisfies this inequality. So, the minimum distance of the code is upper bounded by this quantity. Now, to prove this, we will first consider a linear nk code whose generator matrix is G. Since it is a linear nk code, the total number of code words are 2k code words. So, we will arrange these 2k code words as an array. So, these are your n bit code words, and we will arrange all of these 2k code words as rows of this array. Now, what we are going to show is each in this array there are equal number of zeros and equal number of ones. So, how do we show there are equal number of zeros and equal number of ones? We show it by showing that number of code words that have 1 at the ith position is same as number of code words that have 0 at ith position. And in this way we will show that there are equal numbers of zeros and ones in this array. So, we have a code array where there is at least one non-zero element. Let us denote by S0 the code words that have 0 at the ith location and S1 as the set of code words which have 1 at the ith location. And let us pick up a code word X which belongs to this set S1 which has 1 at the ith location. Now, if we add X to each vector in this set S0 which has 0 at the lth location and X remember has 1 at lth location. If we add these two vectors, because both of them are code word, some of them will be another valid code word which will have 1 at the lth location. Why? Because X has 1 at lth location and this set S0 has 0 at the lth location. So, we will get a new set of code word, let us just call it S prime, S1 prime, which will have 1 at the lth location. So, clearly number of code words which has 1 at that location is same as the original set S0, and this set S1 prime is a subset of the set of code words which have 1 at lth location. Now, from this condition we can conclude that number of code words which have 0 at lth location is must be less than equal to number of code words which have 1 at lth location. Next, what we do is we add this same vector x now to set S1. Earlier we added them to set S0. In the process we generated new set of code words which has 1 at lth location. Now, what we are doing is we are adding this code word X to the set S1. Now, X has 1 at lth location, S1 has 1 at lth location. So, when we add them together we get a new set of code words which will have 0 at lth location. So, we get a new set of code words which we are denoting by S0 prime which will have 0 at the lth location, and number of code words which are in this S0 prime will be same as number of code words which have 1 at lth location. So, from here we can, and of course, this SO prime will be a subset of this S0, the set which has 0 at lth location. So, from this we can conclude then that number of code words which have 1 at lth location is a subset of, is less than number of code words which have 0 at lth location. Now, if we look at this relation 2 and relation 1, here we got the condition that number of code words which have 0 at lth location is less than number of code words which have 1 at lth location, and here we got this condition that number of code words which have 1 at lth location is less than equal to number of code words which have 0 at lth location. Now, these two conditions will be simultaneously satisfied only if both are same. So, from 1 and 2 we can conclude that number of code words that are 0 at a location is same as number of code words which have 1 at that location. So, then you have a 2k cross n this array. So, half of them basically are zeros and half of them are 1. So, you have total. So, each column will have 2k minus 1 zeros and 2k minus 1 ones. And how many such columns are there? We are talking about a code array. So, we are talking about, so these are all code words, these are all code words. So, each one of them are n bit. So, we have total n columns and we have 2 raised to power k rows. So, what we have shown is, so each row will have 2k minus 1 zeros and 2k minus 1 ones, and there are total n such columns. So, total number of ones is how much? N times 2k minus 1. So, what we have shown so far is number of ones in this array is n into 2 raised power k minus 1. Now, what was this array made of? This array consists of 2k code words, right. So, out of those 2k code words, one of them will be an all 0 code word, because we are talking about linear codes. So, remaining 2k minus 1 code words will have minimum distance, minimum weight. Minimum distance is equal to minimum weight of a code word. So, the minimum weight of the code word is at least d min, right. So, number of non-zero code words is given by this, and each one of them will have weight at least equal to d min, because d min is the minimum distance of the code. So, the minimum weight of a non-zero code word must be at least d min. So, 2k minus 1, which is the number of non-zero code words, multiplied by weight of minimum weight of a code word, this number should be less than number of ones in this array. And what is number of ones in this array? That is given by n into 2 raised power k minus 1. So, from this we get this relationship that minimum distance of the code is upper bounded by this, and this is known as Plotkin bound. Finally, we conclude this lecture with Gilbert-Wassermann bound. So, what does Gilbert-Wassermann bound says? If you have a nk linear code whose minimum distance is at least d, then following inequality must be satisfied. And what is this inequality? Says 1 plus n minus 1 C1 plus n minus 1 C2 plus up to n minus 1 CD minus 2 should be less than 2n minus k. So, let us prove this result. So, we know how is minimum distance of a code related to the columns of the parity check matrix. Now, if the minimum distance is at least d, then we know d minus 1 columns are linearly independent. So, no combinations of d minus 1 columns of this parity check matrix will be linearly dependent, right. So, let us construct a parity check matrix H, which is an n minus k cross n matrix. Now, we will try to construct this parity check matrix such that no d minus 1 columns are linearly dependent. Now, if we can ensure that no d minus 1 columns are linearly dependent, then we are ensuring that minimum distance is at least d, and that is what we want to show, that if the minimum distance is at least d, then this condition has to be satisfied. So, how do we construct this parity check matrix H such that no d minus 1 columns, any combinations of up to d minus 1 columns do not add up to 0. So, let us start with first column. Now, the first column of this parity check matrix could be any n minus 1, n minus k tuple, any non-zero n minus k tuple. It could be 1 or zeros, 0 1 or zeros or whatever. It could be any non-zero n minus k tuple. And let us assume that we have chosen I columns of this parity check matrix such that no d minus 1 columns are linearly dependent. Now, if we want to do that, basically we have to ensure that. So, let us look at maximum number of distinct linear combinations of I columns taken d minus 2 or fewer at a time. So, what we are doing is, so we have this H matrix, right, and these are the columns of the H matrix basically, these are columns of this H matrix. Let us say we have constructed I columns. Now, what we are doing is, we are taking linear combinations of 1 column, 2 columns, 3 columns, 4 columns up to d minus 2 columns, right. So, we are taking linear combination of these I columns taken d minus 2 or fewer at a time, and we are trying to find out how many such linear combination exist. So, if I take I columns taken 1 at a time, this is a number that I get I c 1. If I take I columns taken 2 at a time, I get I c 2. Like that, if I consider I columns taken d minus 2 at a time, I get I c d minus 2. So, Ni will give me number of possible linear combinations of these I columns taken 1 at a time, 2 at a time, 3 at a time up to d minus 2 at a time. Now, if this number Ni which we just computed is less than all possible n minus k n tuple, non-zero n minus n tuple. Now, how many non-zero n minus k tuple we have? We have total 2 raised to power n minus k minus 1, because one of them will be all 0 n tuples. So, these many number of n non-zero n tuples we have. Now, if this number Ni is less than this number, what does it mean? We can find another n tuple which would be linearly independent of any of these columns. So, if this number Ni is less than 2 raised to power n minus k minus 1, it means we can add another column which is different from any of the linear combinations of these I columns taken 1 at a time, 2 at a time, 3 at a time, d minus 2 at a time, right. And this will still ensure that d minus 1 columns of this parity check matrix would not add up to 0. In other words, they are linearly independent. So, if we can ensure that this number Ni is less than 2n minus k minus 1, then we can add another n minus k column which would be different from any linear combinations which is basically counted here. And this will keep the property that any d minus 1 columns of this newly constructed H matrix, where we are adding this column, this would not add up to 0. So, this new matrix n minus k cross I plus 1 matrix will be linearly independent. Now, we have to ensure that this property holds for I, all i's, I up to n, because we have, when we are constructing the parity check matrix, we have to construct total n columns, the number of columns are n columns. So, this property that I mentioned here, it should hold for I equal to n. So, we continue doing this. So, what we want is this number ni should be less than 2 raised to power n minus k minus 1, and this should be true for all the n columns of the parity check matrix. Hence, this condition should be satisfied for all the n columns, and that essentially proves our result that if we take base, so if you go back here, so if I put I equal to n minus 1, right, if I put I equal to n minus 1, let us just go back here. If I put I, this should hold for I equal to 1, 2, 3, 4 up to n minus 1. This condition should hold for n minus 1. Then I can add another column which will be the nth column, and still I would not have d minus 1 columns of this parity check matrix adding up to 0. So, this should hold for all I up to n minus 1. So, if when we plug I equal to n minus 1, so what we get is n minus 1 C1, n minus 1 C2 should be less than equal to 2n minus k minus 1, and 1 we can write as, so 1 we can bring it this side, and hence we will get our desired expression, which is this. Okay. This we just want it, we want this linear combinations to be less than 2n minus k. Then only we have an additional, we still have an n minus k tuple which we can add as an additional column of this H matrix. So, with this we conclude our lecture on bounds on the size of the code. Thank you.